Hello, I'm Donghee from the Architectural Structural Engineering Lab at Hanyang University. I will present a presentation on topic mechanical performance of concrete incorporated with triple hybrid of graphene oxide, functionalized carbon nanotube, and nano-silica assessment on the bond characteristic. First is introduction. Recently, research on the use of nanomaterials as concrete mixing materials is increasing. These nanomaterials include CNT, NS, and GO. In the case of CNT, the generation of microcracks is controlled due to the bridging effect. NS promotes the hydration reaction to produce the hydrate and allows the concrete to form a dense structure. GO increases the dispersion when incorporated with other nanomaterials such as CNT and NS. Therefore, it is expected that the non-mechanical properties of concrete will be improved when CNT, NS, and GO are incorporated together. The biggest problem that occur when using the materials as concrete mixing materials is agglomeration. As a result of previous studies, when GO was mixed with CNT or NS, the dispersion increased and the mechanical performance of concrete improved accordingly. In addition, it was confirmed that the better the dispersion, the better the bond strength. Therefore, when triple nano reinforced concrete is used, the agglomerations is improved through GO incorporation, and it is expected that the mechanical properties of the concrete will be improved accordingly. However, there are no research results on the mechanical properties of triple hybrid nanoconcrete, and the bond mechanism between reinforcing bars and concrete has not been identified, making it difficult to apply it to actual structure design. Therefore, this study aims to evaluate the mechanical properties of concrete according to the incorporation of nanomaterials and analyzes the effect of the mechanical properties on the bond performance. To this end, the material performance was evaluated by measuring the compressive and splitting tensile strength, Poisson's ratio, and volumetric strain for each concrete mixture. Later, based on this, pull-out tests were conducted to evaluate the bond performance of various variables. Finally, we would like to predict the bond strength through the equation that reflects the material characteristics of concrete. Next is material test. First, the material test plan. Previous studies evaluating the dispersion of triple hybrid nanomaterials and mechanical properties in cement paste unit were analyzed. When CNT, NS, and GO were mixed at 0.01%, 1%, and 0.04% of the cement masses, respectively, the dispersibility and mechanical properties of the cement paste were found to be the best. Therefore, in this study, based on the research results, the mixing ratio for each nanomaterials was set, and the geomixing amount was set as a variables to evaluate the material performance of concrete according to the incorporation of GO. For material testing, compressive strength and splitting tensile strength were measured according to KS standards, and more than 30 tests were conducted for each mixture. Strain gauges were attached to the concrete specimen in the vertical and horizontal directions to measure the strain, and based on the obtained data, Poisson's ratio and volumetric strain were derived. As a result of the material test, it was confirmed that the splitting tensile strength was the best at 0.04 GCS. The optimal mixing ratio of nanomaterials suggested in previous studies. In addition, Poisson's ratio and volumetric strain of 0.04 GCS were found to be the smallest, which confirmed that the horizontal displacement and volumetric strain of 0.04 GCS were the smallest when subjected to uniaxial compression. Next is pull-out test. Current design codes such as KDS 40, 20, 50, and ACI 318 suggest the development lengths that rivers should be yielded. The anchored development length of river is based on the bond strength, and among the characteristics of concrete, the compressive strength is considered as the main variables. However, the bond between deformed reinforcing bar and concrete consists of mechanical interaction caused by the rib of reinforcing bars, friction between reinforcing bars and concrete, and chemical addition. The chemical addition is resisted at the very small load and then disappears. And the main addition is mechanical interaction and friction. The friction generated when tensile force is applied to the reinforcing bars is affected by the modulus of elasticity and Poisson's ratio of concrete, and the mechanical interaction is mainly influenced by the tensile strength of concrete. Therefore, when calculating the bond strength, besides the compressive strength of the concrete, the tensile strength, Poisson's ratio, and modulus of elasticity of the concrete should be considered. When analyzing the various bond strength equations presented in previous studies, concrete compressive strength, cover thickness, and rebar embedment length are used as major variables. Therefore, in this study, we tried to evaluate the bond strength with respect to the cover thickness and embedment length, and the Proud test was chosen as the experimental method to evaluate various variables. Based on the material test results, the variables of the pull-out test were set. First, in order to evaluate the bond stress due to the incorporation of nanomaterials, the same concrete mixing ratio as in the material test was used. In addition, since the cover thickness compared to the diameter of the rebar is factor that affects the bond stress, the cover thickness was fixed while the rebar diameter was changed. In order to induce splitting failure of specimen, the embedment length of the rebar was set to 3 dB. The specimen pulled out using a screw jack with capacity of 500 kilonewton. To minimize the friction generated on the specimen, a Teflon plate was installed between the bottom surface of specimen and frame. Finally, displacement control was performed at 0.5 mm per minute. This is the evaluation of bond strength according to the cover thickness compared to the diameter of the reinforcing bar and the specimen in which the splitting failure occurred. The splitting tensile strength which is the factor that has the greatest influence on the bond strength, is divided into the bond strength to make it normalized. As a result, As a result, it was found that 0.04 GCS has the highest value in all specimens except for the thinnest cover thickness of 1.8 CS per dB. Also, it was confirmed that the rate of increase in bond strength according to the cover thickness compared to the diameter of the reinforcing bars was 1.14 at 0.04 GCS. This is here. Therefore, it was confirmed that the normalized bond strength increased by splitting tensile strength according to ZO incorporation, and through this, it is considered necessary to consider mechanical properties other than the splitting tensile strength of concrete when calculating the bond strength. In order to analyze the cause of the increase in bond strength for each concrete mixture, the lateral strain generated on the specimen during the pull-out test was measured. These concrete gauges were attached to the test specimens when cracks occurred on the side and splitting failure was expected. The lateral strain in the graph showed the lateral strain at the maximum bond strength of the specimen. The lateral strain at G3, which is the farthest from the loading direction, did not show a significant difference between the formulations. However, the difference became more pronounced as it got closer to the loading direction in G1. In G1, which is closest to the loading point, the strain of 0.04 GCS was the smallest among all specimens regardless of the thickness of the cover relative to the diameter of the reinforcing bar, and it was found to be reduced by up to 76% compared to OPC. This is judged to reflect the material properties of 0.04 GCS, which has a small volumetric strain. Therefore, it was confirmed that the mechanical properties of concrete, such as volumetric strain, affect the bond strength. Last is bond strength evaluation. The summary of the experimental results is as follows. The optimal mixing ratio with the maximum dispersion of the triple hybrid nanomaterials was derived. And it was confirmed that the mechanical properties such as splitting tensile strength, Poisson's ratio, and volumetric strain increased as a result of concrete material tests using this. In addition, as a result of the pull-out test, it was confirmed that the concrete lateral strain for radial stress decreased. Hu et al. Combined the mechanical interaction equation proposed by Tefpers and the friction equation proposed by Timoshenko and Pinchin to propose the following bond strength equation. This formula can calculate bond strength by reflecting the mechanical properties of concrete such as tensile strength, modulus of elasticity, and Poisson's ratio. As a result of calculation considering the mechanical interaction and frictional force, the calculated bond strength of OPC and 0.04 GCS showed an error of about 5% from the experimental value. The calculated value of 0 GCS was overestimated by about 18% compared to the experimental value. For this region, it is considered that the agglomeration phenomenon occurs due to the non-incorporation of GO, and therefore the specimen did not perform properly. In the future, it is considered necessary to propose some bond strength calculation formula that reflects the characteristic of nanomaterials. This is conclusions. First, a material test of triple hybrid nanoconcrete was performed. It was confirmed that the splitting tensile strength increased according to the nanomaterial incorporation. In addition, Poisson's ratio and volumetric strain decreased according to GO incorporation. Next, the bond strength was evaluated according to the cover thickness. As the cover thickness increased, the slope of bond strength changed, and accordingly, other effects besides the material strength should be considered when evaluating the bond strength of a triple hybrid nanoconcrete. Then, the cause of the increase in bond strength was analyzed. The concrete strain due to the radial stress generated during rebar pulling decreased the most at 0.04 GCS. Accordingly, it seems that dispersion affects the bond performance. Finally, the bond strength of triple hybrid nanoconcrete was evaluated. If the bond strength was evaluated considering various mechanical properties, the bond strength could be accurately predicted. In future work, it is necessary to propose an equation for calculating the bond strength according to the mixing ratio of various nanomaterials. Thank you for listening.